The final sequence container we're going to talk about is called a double-ended queue, or a deque. You can remember it's pronounced like a deck of cards. A deque is an extension of the resizable array abstract data type. We can still access and modify elements by their index and add elements to the end of a deque. But in a deque, we can also add and remove elements at the beginning. The abstract data type for a deque consists of all the operations for a resizable array, plus the operations of push front and pop front. So push front adds an element to the front of the deque, and pop front removes the first element of the deque. Let's see how we can implement a deque. Like we implemented a resizable array with fixed arrays, so we will implement a deque with resizable arrays. So imagine two resizable arrays, array left and array right, and put these front to front as in the picture. So you see that array left is drawn backwards. Array left grows to the left and array right grows to the right. In normal operation, pushback and popback are going to be done on the right array, and push front and pop front are going to be done on the left array. Let's see an example of how this works. I'm drawing the arrays here showing the excess capacity to make it more clear what's going on. In reality, we can just use resizable array as a black box in the implementation of a deque. We don't need the internals of how a resizable array is actually implemented in terms of a fixed size array. Okay, so let's see how push front and push back can be implemented. First, say that we want to push front 3. So to push front 3, we can just do a pushback on the left array. And next, say we want to push back 1, we can do that just by pushing back on the right array. Next, say we want to push back 7, again, we can just push back on the right array. And say that we want to push front 8, then we can just do a pushback on the left array. Okay, so you see that we inherit the complexity of all these operations from that of the resizable array, so all this can be done in constant amortized time. If we want to keep track of the size of a deque, that's easy. It's just the sum of the sizes of the left array and the right array. So again, this is constant time. To access and modify elements by their index, we just have to do a little bit of arithmetic. If the index is less than the size of the left array, then the element that we're looking for is going to be in the left array. So we just have to be a little bit careful in computing the location in the left array because this array is working backwards. The last element of the array is in index 0. But I give the formula here, but the details aren't so important. If the index is larger than the size of the left array, then the desired element is in the right resizable array. And the element that we're looking for is given by the equation at the bottom of the slide. So size, get, and set inherit a constant time implementation from their constant time implementations in a resizable array. Okay, now let's look at the interesting case. So you knew there had to be a catch somewhere, right? Say our deque looks as above, and now we pop front. Okay, so no problem. We just do a pop back on the left array to remove the 3. So now the left array is empty, and say that we want to pop front again. So that is, we want to remove the 1, the first element in the right array. But removing the first element of a resizable array is not in our abstract data type for a resizable array. So we could do it, but it's a very expensive operation. Do you see any other way that we could proceed? When one of the arrays becomes empty, then we can rebalance the elements so that roughly half are in each array. So in this case, there are 3 elements in the right array. So we can rebalance so that there's 1 element in the left array and 2 elements in the right array. In general, we could put the floor of n over 2 elements in the left array and the ceiling of n over 2 elements in the right array. Rebalancing is similar to when we doubled the size of a fixed size array in our implementation of a resizable array. So when we doubled the size and then we had to copy all the elements over. It's an expensive operation, right? The time it takes is proportional to the number of elements in the array. But we can again argue that this rebalancing operation does not happen too often, so that the average time of pop front averaged over any sequence of push and pop operations will be constant. In other words, we can argue that the amortized complexity of pop front is constant. Of course, the same thing is true for pop back, but for this example, I'm just going to focus on pop front. So let's see why the amortized complexity of pop front is constant. Say that the deck has n elements, and we just rebalanced. So now the left array has the floor of n over 2 elements, and the right array has the ceiling of n over 2 elements. We want to average the cost of pop front over the number of push and pop operations we do until the next time we have to rebalance. And we also include the cost of this next rebalancing. So let t be the number of push and pop operations we do until the next time we have to rebalance. When we don't have to rebalance, we know that the pop operations can be done in constant time, and the push operations can be done in constant amortized time. So the total time until the next rebalance is at most a constant times t. So say that the next rebalance occurs because the left array becomes empty. So at that time, the number of elements in the deck will be equal to the size of the right array because the left array is empty. So say that S is the number of elements in the deck at that time. So the time it takes to rebalance will be proportional to S because we're going to have to copy over about S over 2 many elements and shift S over 2 many elements in the right array. So now we've argued that the total time of all the push and pop operations plus the time to do the next rebalance is at most a constant times the sum of S plus t. So to show that the amortized cost of pop front is constant, it suffices to show that S plus t is at most a constant times t. Because a constant times t averaged over t operations gives a constant. So we're going to show that t is actually at least s minus 1. Let's see why this is the case. So to empty the left array, we must do at least the floor of n over 2 many pop front operations. We must also do at least the absolute value of s minus the ceiling of n over 2 many push and pop back operations to change the size of the right array to be s. So thus the total number of push and pop operations that we do is at least the floor of n over 2 plus s minus the ceiling of n over 2, which is at least s minus 1. Okay, so let's just summarize what we've shown. We do t push and pop operations until the next time that we have to rebalance. We know that each of these push and pop operations takes constant amortized time. So the total time for all these operations is at most a constant times t. When we have to rebalance, we're going to have to spend time s, which is the number of elements in the array at the time of the rebalancing. So the total time for all these push-pop operations plus the time to rebalance is at most a constant times t plus s. And now we've just shown that t is actually bigger than s minus 1. So a constant times t plus s is still just a constant times t. So the total time to do all these push-pop operations plus the rebalancing is a constant times t. And we did t operations, so therefore each operation on average just takes constant time. Okay, so now we've seen how to implement a deque with two resizable arrays. The time for get and set is constant, and the time for push and pop on the front or back of an array is amortized constant. For the push operations, this is purely inherited from the amortized cost in a resizable array. For the pop operations, we needed a new argument. These were amortized constant time because we periodically have to rebalance the resizable arrays when one side becomes empty. But we've argued that we have to do a lot of operations in between each rebalancing so that the amortized cost is constant. The way that we have described implementing a deque is actually not how it's done in the C++ standard library. In fact, the implementation with two resizable arrays that we described is not allowed by the C++ standard, because the standard states that references to elements cannot change in a push front or push back operation. References would change in a push front or push back operation in our implementation with resizable arrays when one of the push front or push back operations was done in the case where the fixed size array underlying the resizable array had no capacity. And so in that case, we would have to allocate a new array and copy the elements over, thereby changing the references to those elements. So the way a deque is typically implemented in the standard library is via a linked list of pointers to fixed size arrays. When all these fixed size arrays are full and we do a push front or push back, we simply allocate a new fixed size array to hold the incoming element. In this way, none of the elements already in the deque need to be moved, so their references are not invalidated.